hackers make use of these loopholes to attack users, steal your credit card details, pretend to be some very safe website, but you can grab whatever you can. Let's have a look. Okay? This is the client side, and in the hard drive, there's an entry that corresponds to a cookie file from eBay. A cookie file comes with some number. It's going to be more complex than this. So this client, a web browser, wants to communicate with the server Amazon.com. Okay? So it's going to request by sending, say, an HTTP GET command. In the Amazon server, once it has accepted this HTTP request, then that server is going to create a unique ID for that particular user. At this stage, the Amazon server doesn't know the name of the user, but it can detect what is the IP address of that user. Okay? So it can, locate that person. Technically, you can do that. This number will be stored in the backend database, and this number will be associated with whatever activities this user will do later on. So after creating this number, it's going to send to the client, okay, please set this cookie in your browser. It comes with a number. Now if the user accepted that cookie, a cookie will be stored in the user's hard drive that is managed by the web browser that corresponds to Amazon. Okay. Thereafter, any subsequent HTTP requests will come with this cookie number, okay, to help identify the user from among many other customers that this server is talking to. So the server will be able to tell, okay, this is another message request coming from this user who purchased $2,000 worth of products from us. So it can do that. Okay? And the server, typically nowadays, servers are more sophisticated. They make use of AI, artificial intelligence, to try and predict, okay, what other products would you be interested in? And interestingly, for instance, we're taking up neural networks, AI. There's a neural network architecture called restricted Boltzmann machine, and it can compute for what other products you might be buying from them. So 1 week later, let's say Susan decides, I want to go back to this Amazon platform, and I think I'm ready to buy this product. Automatically, the web browser will pick up the cookie number associated with the web server. So it's going to pick the same number, and in the server side, it's going to be able to identify, oh, this user came back. Okay. Perhaps we can offer some discount, something like that. So cookies can bring the following services. It can help. Help implement an efficient authentication scheme. Okay. If, for instance, this server is your email server and it is running using HTTP, initially you need to authenticate yourself to that server. You need to provide your username and password. But each time you're trying to get an email from the server or changing to another folder, you don't want to keep on typing your password. So a cookie file will contain that information that tells the server, this user has been authenticated already. So it is safe to transmit these emails. So here, HTTP is able to implement stateful sessions by storing very important information about the user in both the server side and the client side. However, cookies could be used for attacking clients. Okay? If, for instance, you agree to type your username, get your real name, your address, your credit card details, this information could be encrypted and stored as So you don't have to keep on typing your credit card details every time you're trying to shop using that, using that server. But there are always some loopholes. If you're wondering, let's say HTTPS, can we capture these messages using Wireshark? You won't be able to capture the contents of HTTPS in clear text. It's going to be encrypted. But all we know is that all these packets will be using a standard port number 443. So you can at least still look at these encrypted packets if you wish to investigate. Next, let's talk about web cache and proxy server. This technology is used together with HTTP. How can we speed up requesting for an object if the origin server is, let's say, in the US? Not so long time ago here in Massey, in order to get internet connection, you need to customize your browser to point to a specific web cache or proxy server. Starting this semester, maybe early this year, they don't require us to do this anymore. I'm just wondering, have you noticed that? Massey's network has changed just recently. But since this is our topic, it's good to learn about what does a proxy server do. Okay? So before you can type al-cache massey.ac.nz, and the setting is requiring that you should type port 8080. Or if you don't know the actual server name, proxy name, you can use this HTTP get proxy, and this is going to point you to the actual server name. Nowadays, we don't do this anymore. Nowadays, we have a transparent proxy server that we don't know how it's configured. Perhaps it's due to security reasons. Massey does not allow you to pinpoint the name of that server anymore. So what happens? You've got a proxy server. You say, here we are at Massey. You want to download the web page. You say you want to look at the latest news. The client will contact this proxy server. And if you want a web object coming from a server across the oceans, across multiple oceans, then this proxy server, on behalf of the client, will contact that origin server, get that object, and also store a copy of that object into its hard drive, and then send the reply back to the user. A proxy server is a network entity, typically a simple PC, simple Linux workstation that runs some open source proxy server program that satisfies web HTTP requests on behalf of an origin server. If, for instance, this client wants to retrieve the latest news, let's say New Zealand Herald, okay? And it has received that request. This proxy server will store that information, and if another client wants to get hold of that same object, the web proxy server is going to check, do I have that object already? If yes, it's going to immediately send that object without going back to that origin server. Now let's talk about the advantages of using web proxy or web cache using the following context. Let's say you've got an institutional network, say Massey University. We've got an Ethernet LAN here, and in this local area network, we've got a web cache. Okay. And in order to avail of to connect to the public internet, okay, our access network will have to get the services of a provider ISP. We know that they need to pay, the price they pay is typically commensurate to the amount of traffic they exchange with that ISP. But we can see here that the local area network is relatively fast. The bandwidth is 100 megabits per second. But between this gateway router and the next router that connects to the public internet, you have this access link, which is only 15 megabit per second. Now, every time a client wants to retrieve some object from the public internet, without the web cache, that request will have to go through this bottleneck link, and it's going to take some time, some significant amount of delay for that object to be retrieved. Okay. So using web cache, we will see that it can help reduce the response time to satisfy an HTTP request. It can also reduce the amount of traffic exchanged between the access network and also this bottleneck link, okay, the access link. And in general, it helps improve the services provided by content providers. And this web cache will store everything, including objects requested via peer-to-peer. We'll do a bit of math, okay? Let's look at this simple network again, and let's estimate the total delay. If you have this word LAN, you have this bottleneck link, you have the public internet, and you've got the following assumptions. We can compute for the total delay. Let me explain this by going to the board. Okay, first, we're given that the object requested by these clients comes with an average object size of 1 megabit per request. 1 megabit per request. One megabit, we can write it as 1 times 10 to the 6 bits per request. That's the average object size, and we're also given that the average request rate coming from these clients is 15 requests per second. And we're also given that the average delay to satisfy any request coming from this internet router to any of the origin servers anywhere in the globe, okay, until that object arrives at this internet router is, let's say, 2 seconds. Let's call that internet delay. Let's call this L, the size of the object. And this is, let's call it A, the rate of arrival of requests. And from our previous discussions, we found this interesting formula, LA over R, which is all about traffic intensity. That means we can put, these parameters together, and we can estimate the traffic intensity. If the traffic intensity approaches 1, if it approaches 1, then it's telling us that eventually packets will be queuing up in the intervening routers, causing so much delay. Now, for this particular network, we need to estimate the delay. Okay, we need to estimate the LAN delay. We need to estimate the access link delay. And we need to consider the internet delay. We need to try and put them together. Okay? Because when a request comes from, is coming from a LAN It may involve the access link as well as the internet delay. So what is that average total delay? Okay. Let's look at the LAN delay first. So we can substitute all the parameters to this traffic intensity. Okay. L is 1 times 10 to the 6 bits per request, multiplied by 8, 15 requests per second. Then for this particular LAN, we know that it is relatively fast. Okay. From the past, from the previous slide, let me see, it's telling us that it comes with a bandwidth of 100 megabits per second. So this LAN is bandwidth 100 megabits per second. Here we're going to have 15 megabits per second. For the internet, we just know that it is going to give us an average delay of 2 seconds. So the R for this, for LAN, the R is equal to 100 megabit per second. Mega times 10 to the 6 bits per second. So you can see that this request, we can look at the units. Okay. Bits per second, they will all cancel out. Okay. You have here times 10 to the 6, times 10 to the 6. You can cancel it out. 1 times 15 divided by 100. That's going to give us 0.15 as the traffic intensity. Traffic intensity here is 0.15. Any number less than 1 is a good sign that this is not going to amount to any significant delay. Okay? It is so much less than 1, this is going to amount to tens of milliseconds of delay. Tens of milliseconds. So no problem in the LAN. Now we can look at the access link delay. So using the same strategy, obviously it comes at a lower bandwidth. So if you plug in all the parameters in the same formula, LA over R, we will end up with the same 1 times 10 to the 6 bits per requests, multiplied by 15 requests per second. But the R is now equal to 15 megabits per second, megabits per second. It's not bytes. You need to remember that we're not using the bytes as a unit here, but megabits. So bits per second, no. The bits per second here cancels out. Then we will have times 10 to the 6 cancels out. Then we have 15 over 15 is equal to 1. So this is relatively high traffic intensity because as traffic intensity approaches 1, packets will queue up, causing delays that is commensurate to minutes of delays. Minutes of delay. Now, when you put them together, okay, tens of milliseconds of delay, we also have here minutes of delay, and we have 2-second delay. If you put them together, that's a lot of time. So the clients here will not be happy. If you're trying to download some web object from Europe, has to go through all these channels, you need to wait for minutes. And, that's very productive. So the question is, how can we improve this network? Okay? You can see that we've got a bottleneck link here. If you're going to upgrade this bottleneck link to, let's say, 100 megabits per second, sure enough, it's going to improve the performance at a very costly upgrade. The university will not be very happy to do that because it's going to pay a higher monthly fee. Okay? So this is changed to 100 megabits per second. this is no longer minutes of delay, this is going to be milliseconds of delay. The total delay will still be about 2 seconds plus a few milliseconds. This is after doing a very costly upgrade. Upgrade the link back, the bottleneck link. Now let's talk about case number 3. Let's say we're going to install a web cache in the local area network. And we're going to keep this bottleneck link to be 15 megabit per second. Now the cost of this web cache, as I mentioned, you need to buy a simple PC, a decent PC, and then install Linux, and then download an open source proxy server program and run it. Okay. Now what's going to happen? Now there's this statistically, empirically derived data that tells us that if you have a proxy server here, typically the hit rate is between 0.27 to 0.7. That means between 20% to 70%, this web cache will be able to satisfy all HTTP requests coming from your local area network. This is of course assuming that they're all doing something related to their work. Otherwise it could be anything. So let's say that 40% of the requests coming from the clients could be satisfied by this web cache. What will be the estimated total average delay? So we can do some quick math here. So it's still 15 megabit per second. So initially you've got minutes of delay here. Here we've got 2 seconds. And according to the analysis, 40% of the time, the request could be satisfied by this line. Okay. Then 60% of the time, it has to go through the bottleneck link as well as the public internet. Okay. 60% of the time. So we can do a simple math. Okay. Instead of just 2 seconds, we need to compute for 60% of 2 seconds. That's 1.2 seconds. So it's no longer 2 seconds then. What about this 15 megabit per second? If we're using 15 megabit per second, we know that the traffic intensity is equal to 1. If it is being used 100% of the time, but this is going to be used 60% of the time. So we will have 1 times 0.6, it's equal to 0.6. So now the traffic intensity in the access link is now equal to 0.6, which is less than 1. It's no longer minutes of delay. This is commensurate to milliseconds of delay now. So we can put them together now. If let's say, just to give it a number, we can say, let's say 10 milliseconds. So we can write it as 0.0123, 0.01 second. So this will incur 0.01 seconds. This will incur 1.2 seconds. And this will incur the same thing. Because it's going to be 40% smaller. So here, we know that this is going to incur tens of milliseconds if used 100% of the time. But it's going to be 0.4%, 40% this time, 40% of 10 milliseconds. 0 point, it's going to be very small. If you put them together, we will be facing only a very small delay of 1.21 seconds. And 1.21 seconds is smaller, it's a shorter delay, total average delay, as compared to doing a very costly link upgrade that will still incur an average total delay of 2 seconds plus.
I'm wondering, why does the latency jump from minutes to when it's only 6% to milliseconds? How does that exactly work?
This one, okay. So if we're going to use this bottleneck link 100% of the time, we saw from our computation that it's going to give us traffic intensity of 1. That's for 100% of the time. If you use 100% of the time. And if we're going to use it only 40% of the time, sorry, 60% of the time, if you use 60% of the time, then the traffic intensity is now equal to 0.6. And how did we get the milliseconds from 0.6? It's from empirical data. That's the confusing part. So according to research, if the traffic intensity is about even 0.8, for as long as it is less than 1, up to 0.8 is going to incur milliseconds of delay. 0.6 is still lower than, it's even lower than 0.8. So that's the reason. Any other questions? So this is, of course, justifying that using web cache will benefit both the network and the users without paying so much. Okay, let's talk about how this web cache, this proxy server works. Okay, let's look at some scenario. Okay. So I got this from Mozilla. Okay. So let's talk about a client contacting a web cache, and this client is trying to download some document. Hopefully it's big enough. Get some document. Okay, it's a GET request targeted, destined to this web cache. Initially, the web cache is empty. It didn't store any previous requests. Okay. So the web cache will have to make a request on behalf of the client. So it's going to contact the origin server directly. Once it receives the actual object from the server, from the origin server, it's going to store it into its hard drive. So copy the object in its cache. Okay? Then, according to the server here, this object has a maximum age of 100 seconds. Maybe it's all about some news. So it's going to get stale after 100 seconds. Okay. Now, this client will eventually receive that object. So there's a specification that the object contained in this message has a maximum age of 100, and at the moment, its current age is 0. Next, 10 seconds later, another client requests for the same exact object. Now the web cache checks to see, okay, I have a copy of that object. The maximum age is 100, and the current age is 10 seconds because it's 10 seconds later. In this case, if the object is still fresh, it's going to send a copy of that object to the requested client, and here the client will have to take note that the age of that object is 10 seconds. Now let's say 100 seconds later, another client requests for exactly the same object. Maybe they're interested in finding some specific news. Okay? 100 seconds later, that object is already stale. The age of the object is now 110 seconds, but checking the maximum age is 100. It is greater than the maximum age. Therefore, this web cache will have to request, it's going to ask for that object from the origin server with the following condition. So here, the web cache is asking if none of your objects matches this e tag value, please send me the new copy. Okay. What is that e tag? An e tag is a fingerprint for an object. So you can think of it as a hash value, but it's computed by a more sophisticated hash function. Okay. If none matches this e tag value in your cache, in your own in the origin server's directory, then it's asking, please send me the new copy. Now let's say the server determines that, okay, it's still a fresh copy, it was not updated. That origin server could reply, HTTP 304, that object was not modified yet, so please, send whatever copy you have. Okay? But it's going to reset the H field in this case, that object becomes fresh again. Then eventually client will receive that object. Oops, sorry. I'll just stop it. I should turn my Another possibility is to make use of if modified since header. Okay. So the cache can ask the origin server, if this object has not been modified since this date, please send me a new copy. Okay. Let's have a look. So the web cache requests for, let's say, an object named kiwi.gif, and it comes with this header. If modified since this date, please send me a new copy. The origin server is going to check kiwi.gif in its database. If it was not modified, then it can say, you should have a fresh copy, or in this case, not modified. It's going to send HTTP 304, not yet modified. So please send whatever copy you have to your requesting client. If the object has been modified since the given date, then it's going to send a new copy of that object. Okay? And it's going to send this numeric code 200. In practice, you will find if modified since, if none match, put together. Okay? And there are many possible combinations of header fields to indicate to the server, okay, do we have a new copy, a better, improved version of that object? Okay. There's so many ways of doing this. Okay. And I did some experimentation. For instance, let's say I'm requesting for this HTML file, and I captured the packets using Wireshark. You can see get, followed by the URL, followed by that object. And later on, I tried requesting for the same object from the same web server, and I could see from my captured packet, if none match, then if modified since they come together. So this is how the exchange of objects could be made more efficient by using this combination of header fields. It's what's going on, and the web browser is doing that on our behalf. Now, if you're using internet banking, it's very important that you clear your browser's cache after looking at your bank details. Okay? Of course, everybody must be familiar with this one. Better yet, it's good to switch to incognito mode or private window mode. But that the incognito mode is 100% foolproof? Unfortunately not. That's what you will see. If you look at the Mozilla developers website, you will see that there are still some loopholes. Okay. And you might be wondering, can a web server instruct a web browser not to cache the web objects? If, for instance, you're accessing your bank accounts through ANZ, ANZ's web server will actually instruct your web browser, please do not cache this information because it could be used for future attacks. Okay? But of course, it depends on the web browser to follow the instructions. What you will find is that they can add header fields that says pragma no cache. This is one of the header fields in the HTTP reply. Okay? Cache control, no store. And we can actually investigate this. We can see for ourselves that if you do so, you'll be able to see what the browser is doing. Okay, let me do this demo. This time I'm going to use Mozilla, an older version of Mozilla. And what we can do, okay. For instance, I can check what is the configuration of this browser. Config. Here you can see it's telling me, here be dragons. Changing these advanced settings can be harmful to the stability, security, and performance of this application. So you can see, and I'll be careful, I promise. And then you can see the settings, the prop. If you want persistent connections, how many persistent connections, all of these parameters can be found here. Say keep alive. If you look at keep alive, there you go. You can see what is the timeout. You can change this timeout. Instead of 115 seconds, you can change it to whatever you like. It's the same thing. And yeah, I don't memorize all these parameters, but it is possible to modify them. But today we want to see the cache. Okay. Cache. So there's a cache here. We can look at the entries. What do we have? Okay, this is in the storage. You see everything I access, is stored in its cache. In case, so there's a cache in your browser, and also there's a cache in the web proxy server. Okay. And of course we can clear it. Okay, let me just clean it up first. Then we can do a bit of investigation. Clear now. Okay. If I run about cache, it shouldn't show too many anymore. So you can see it's 0 now. Number of entries 0, number of entries 0. Then I'm going to go back to my own server because I've got full control over the server. And just to help the class understand what's going on, I can customize the way my server sends its reply. Okay. If, for instance, I say, okay, I'm going to use allow caching. Okay, I'm going to disable this. I'll tell the class, in a few minutes what's going on. Here it's an overly simplified HTTP request. If, let's say, my server detects that the web browser is requesting for some image, and that image file is in my hard drive, it's going to say HTTP 1.0.200, positive completion reply, it's okay. Okay, the content type is image, or GIF. And then later on it's going to actually transmit the data. This is going to allow caching. Okay. Then we can do a quick test. I'm going to, because I modified the program, I need to recompile it. Save, recompile. Then I'm going to go to that folder. Maybe just a folder. Maybe just clear it. Then run that server again.